All right, welcome everybody to today's webinar hosted by the International Solar Energy Society and by the IEA SHC Solar Academy. We are very pleased to have all of you here, and we are especially happy to welcome back the IEA SHC Solar Academy for 2019. We have had a great cooperation between ISES and the IEA SHC, and we are looking forward to many more exciting webinars this year. Today's webinar will present the IEA SHC Task 55 on the topic of large-scale solar heating and cooling systems integration into district heating and cooling networks. And we have a total of 5 speakers joining us for the webinar and presenting their work. For this, today's webinar will last 1.5 hours and will of course include a Q&A section. My name is Arabella. I am the Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on this webinar today. The International Solar Energy Society ISES is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES as a member, and you can find out more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings, such as today's, in the ISES webinar archive. ISES members can also get discounts and even free registration to ISES events and partner events. Every month, ISES publishes a newsletter for our members where you can follow our progress and share your news. Members can also subscribe to our academic journal, Solar Energy, which is our flagship publication. And in the ISES online bookshop, ISES members qualify for reduced prices on the different publications. So we welcome those who are not yet members to join today to support our work. For those who already are a member, we thank you for your support. Now, for some brief information on the webinar and especially the Q&A section before we start. During today's webinar, our expert speakers will present the IEA SHC Task 55 and will introduce different projects on this topic. This will be followed by a Q&A section for you, the audience. For the Q&A section, we invite you to send in your questions, and we are looking forward to your participation. When sending in the questions, please write who the question is for and keep your questions short and precise. Please feel free to start in sending your questions anytime throughout the webinar. I am now happy to introduce our moderator for today, Bärbel Epp. Bärbel Epp will be the moderator for all Solar Academy webinars with ISES in 2019. Bärbel is the founder and managing director of the HSC Solar, a solar market research and international communication network for professionals worldwide. She graduated in physics and looks back at more than 20 years of journalism in the field of solar thermal energy. Now, I am happy to hand over to Bärbel. Bärbel will guide us through the discussion and also moderate the Q&A session with your questions. Bärbel, thank you very much for joining us. The floor is yours.
Thank you, Arabella. Welcome to all our participants for this first webinar in the series of Solar Academy webinars that we organize very successfully in close cooperation with ISES since 2017. Well, Arabella will hand me over the screen, I think, and I will have a short introduction on the IEA Solar Heating and Cooling Program. Thank you. I hope this works, yes. Well, the IEA Solar Heating and Cooling Program is the framework of this Solar Academy. It's a project-funded international R&D collaboration, which includes more than 400 experts from 5 continents. In the map, you can see the 20 member countries, which are marked red, and a lot of more countries which are indirectly member of this research program via sponsors and partner organizations in yellow and orange. Currently, the IEA Solar Heating and Cooling Program runs 7 research platforms on a large variety of topics, from storage, solar building envelope technologies, PV thermal solutions, renovation of historic buildings, and solar solutions for industrial water management. The Solar Academy was founded to spread the knowledge and the results of this comprehensive international research network with experts around the world. So we organize these quarterly webinars with ISES. We also have a big number of videos online from conferences, experts' videos, and presentations. We organize national days, which are usually attached to biannual executive committee members that take part in different countries. And we organize on request of member countries trainings, two-day trainings, which recently took part in China, South Africa, and UK. So altogether, you find the informations about and results and studies from the different research platforms on this website, IEA-SHC.org. You can, for further questions, always contact the Secretariat at this email address, and you can for sure follow us on social media. So this is it from my side. We have today a very exciting topic on large-scale solar heating and cooling systems integration into district heating and cooling networks. This is a very dynamically developing segment, as it is more and more recognized by municipal decision makers as well as federal governments that renewable and particularly solar district heating is the most cost-effective and fastest way to decarbonize the heating sector. This is why a growing number of countries support this technology with investment subsidies or support structures. Among them is Germany, Austria, France, Spain, Netherlands, Slovenia, and China. So what we have seen in recent years that besides the established solar district heating countries, which are Denmark, Germany, Austria, and Sweden, we have seen new markets coming up with interesting demonstration plans in Serbia, Latvia, Italy, Netherlands, France, and China is actually supporting district heating in some of their provinces, which is Tibet, Shandong, Inner Mongolia, and Hebei. So you see that it's a dynamically growing and very important subject for heat transformation. And so I would like to introduce our first speaker, which is Dr. Sabine Putz. She is the head of Task 55. So she is sort of the coordinator of this international research project, and all the 5 speakers of today's webinar are part of this research group. Sabine is head of the R&D department since 2009 and CTO since 2015 of the Austrian turnkey solar heating and cooling system supplier Solid. She is involved in a number of national and international research projects, and well, she will present the structure and the objectives of this research program, which is called Task 55. Welcome, Sabine, and thanks for your presentation.
Hello, can you hear me?
Yes.
Okay, fine. So I'm not a doctor, I have to say. I'm only a chemical engineer, but it's no problem. Thank you, Bärbel. So my name is Sabine Putz, as Bärbel said, and I'm the operating agent of Task 55. And also I'm working for Solid since more than 10 years as head of R&D. And maybe you know Solid. If not, Solid is a turnkey engineering company for large-scale solar thermal installations and solar thermal systems. So today you will hear a lot of information about Task 55, which is dealing with the integration of large-scale solar heating and cooling systems in district heating and cooling networks. And the future generation of district heating systems is built on a lower temperature levels in the distribution networks. In the moment, only in a few countries, district heating is operated at lower temperature level. So for higher solar thermal shares, the development of low temperature nets, they are called the 4th generation of district heating, are need to be built. Here you can see the solar district heating installations in Europe. There are about 300 plants around Europe. The production is about 660 gigawatt hours, and yearly come 30% new installation come up. So why task 55? Task 55 is the successor of task 45, which was dealing with generally large-scale solar thermal installations. And the need for the task is to substitute fossils and pushing the overall energy efficiency in urban areas for district heating and cooling. And also the step from megawatt installations to gigawatt systems needs to be described. And what we further need are systems at low costs. We need a reduced heat price, and we need validated increased collector field efficiency and output. Task 55 is not a research project. It acts as an exchange platform for interested stakeholders and experts from research and industry. So these are the short facts of the task. It started in 2016 and will end in August 2020. We have around 65 experts, and more of 60% of these experts come from industry, so this is very special. The access to more than 35 project results will be the output. So the output is fact sheets, and they will be produced in the end of the project time. So we have 2 expert meetings and workshops each year, and in the moment 12 countries are participating: Austria, Canada, China, Denmark, Finland, France, Germany, Italy, Spain, Sweden, the Netherlands, and United Kingdom. And we have a close cooperation, or moderate cooperation, would say, with the IEA technology platform DHC, District Heating and Cooling. Especially we work together with the DHC Annex TS2, which is dealing with the 4th generation, the lower temperature generation of district heating. The task is divided in 4 subtasks. Subtask A is led by Ralf Roman Schmidt from Austria, from the AIT, and deals with network analysis and integration. Subtask B deals with components testing, system monitoring, and quality assurance, led by China, by Zhao Jingdai from Sunrain. Subtask C is dealing with the system design, led by Jan-Erik Nielsen from Plan Energy from Denmark. And Subtask D deals with economic aspects and promotion. It's led by Germany, by Solides, Miss Magdalena Berberich. So these are the objectives on one slide. The objectives are to describe low-cost and high-performance large-size solar district heating and in future solar district cooling and their main components. And the integration of large seasonal storages will be simulated. Then all the crucial components for modular conception and construction of this large installation will be described. Further, we will elaborate business models and also financing calculation models. And the measurement methods of tests on field collector performances will be validated. Then further, we will produce country reports, feasibility studies, and the best practice database for large-scale solar district heating. Yes, and again, the cooperation with the DHC technology program. Here you can see a very big installation in Denmark. It's in Vojens, 71,000 square meters. And in the back, you can see here the seasonal storage, but it's not filled at this time. And this is another installation, which is pretty new. It was It's operating since November 2018, and it's in Tibet, about 22,000 square meters collectors and also seasonal storage. And they have a low temperature district heating net, and very special is that all components of these installations are from Europe. And the most special thing is that China's government is 100% sponsoring this project. So China shows us how it can work. These are the trends of solar district heating. So Denmark infects several countries around the world with their large installations and their long-term experience. And a further trend is to maximize the solar thermal share and to eliminate barriers and to find the opportunities for solar thermal. And then further development of more seasonal storages concepts. Then we need to define model-based control strategies for the whole system, not only for the solar thermal, but for the whole system, including the district heating net. And then it's needed to design a solar thermal system, including hybrid technology. With hybrid technology, we mean seasonal storages, biomass, or waste heat, or interactions with CHPs. So I'm at the end of my presentation. I will tell you where our next meetings will take place. In 2 weeks, we will have our 6th meeting in Spain, in Almeria, from 8th to 10th of April, and we will have an interesting technology tour to the platform of solar platform of Almeria. It's a very big testing platform for solar collectors. And the 7th meeting will be in Sweden, in Härnösand, not in the end of September. It's pretty new. Since yesterday, we know that it will be from in the 1st week of October. We will send out the date soon. So if you want to participate in one of these meetings, just please contact me. And this is a picture of the working group. It's from 2017 in Abu Dhabi. Yeah, and then I'd like to say thank you for listening and follow us on Twitter. Thank you.
Thank you, Sabine. This was a very nice overview of this comprehensive Task 55. And our second speaker, Jan Erik Nielsen from Denmark, was already presented and showed up in your presentation. He supports Sabine in Task 55 as subgroup leader, and he's responsible for the design of solar thermal systems and hybrid components. He has long-term experiences in the field of solar heating and cooling, and works as project engineer at the Danish company Plan Energi. And he was heavily engaged in standards and certification matters of collectors and systems on the global level in the last probably 20 to 30 years. So Jan Erik, yeah, we will have the Q&A session at the end, as Arabella said. So please type in your questions while the speakers do their presentations. And I welcome Jan Erik for his presentation on seasonal storage of solar district heating experiences from Denmark. Please.
Thank you very much, Bärbel, for the nice introduction. And hello, everybody. I would like to share some experiences from Denmark on large seasonal storages. I'm working with the company Plan Energi, a small consulting company based in Denmark. We are 40 people, but we have long-term experience with renewable heating, especially district heating. Coming to the storage, we see these large heat storages as a very important component in the future energy systems, because having these storages, you have the possibility to couple the electricity sector with the heat sector. There can be interaction via heat pumps and combined heat and power plants. So these heat storages can then help levelizing the dynamic electricity production from wind turbines and PV fields. But today I will not go into all this system, but I will focus on the interaction between, or the connection between, the solar thermal collector fields and the large seasonal storage. So why do we do this in Denmark? Yeah, because we want to couple the electricity sector with the heat sector. We have a lot of wind turbines in Denmark. More than 40% of our electricity production is from wind. So we have the need for this, and we have been working on this for some years. You see to the right this figure of prices in euro per square meters of collectors, depending on the years. So we have been working on this for almost more than 20 years actually. The black squares are the systems with the seasonal storages. So you see, back in time they were quite expensive because it was demonstration, and you need to accept higher expenses there. But as time goes, these prices are coming down and are now at the level as the simple systems. So the red dots are systems with having no seasonal storage, but only maybe a small storage. The next figure here is the heat price. So this is in euro per megawatt hours, and you see here, of course, the same tendency. The x-axis is here the size of the system. So we have very large systems now. We have most experience in so-called water pit storage, which is a simple storage where you just dig a hole in the ground and you put the soil from the hole to the sides. You put a foil inside this hole and you fill it with water, and then on top you put an insulated lid. An example of that you see here in Marstal. So this is 75,000 cubic meter storage. To the right we have a picture during the excavation. You see these large machines seem small in connection with the storage size, and this is then to the left we have the final storage covered with the lid. This storage serves in total 33,000 square meters of collectors. We have done some measurements. So on this system we have a solar fraction of 35%, and they claim to have a renewable energy fraction of 100% because they fire with biomass. If we look then on the energy balance on the store, we see here storage efficiency of 66%. So this means that 34% is lost. We have the temperatures between 20 and 82 degrees. Another example is in Dronninglund. Here we have 60,000 square cubic meter pit heat storage, serving 38,000 square meters. You see the collector field to the left here, and the storage is actually integrated in an old gravel pit. And to the right you see the whole system. Here we have a solar fraction of 40%. And what is very interesting in this case, when you look at the heat balance for the storage, we have actually a storage efficiency of more than 90%, so the heat loss is less than 10%. So this is very encouraging, actually. So that's the annual heat loss is only 10% of the energy output. You see here a low minimum temperature, so there's a heat pump which is lowering the temperature in the storage in the winter and in the springtime, and this is of course part of the explanation of the low storage heat loss. We have more pit storages, but we have not in Plan Energy been involved in these systems, but they have very large storages between 100 and 200,000 cubic meters. Looking at the prices, so if you make them big enough, you have a cubic meter price of around 30 euro. So this is not very expensive actually for storages, energy storages. This is a very cheap price. We have one demonstration project of borehole storage for solar energy. This is demonstration size only. But you see here the model of it. So we have pipes in the earth, and you see on the next picture here that we put the heat down in the earth, and then in the summer, and then we can extract it in the winter. Also here we have a heat pump. If we look at the heat balances here, so here we have a solar fraction of 22%, and you see in the circle around the storage, it's only a small size storage. It's only a small part of the energy going to this storage. And this is also seen on on the storage efficiency, because the bigger the storage is, the larger or the bigger the storage efficiency can be. So here we have only a storage efficiency of 50%, but compared to the size of the storage, it's actually quite good. Looking at the prices here, we have maybe not so much experience, but we think we can go down to, in the future, if you make it big enough, we can go down to $5 per cubic meter, and this is also a good low price. You should consider here that this is per cubic meter Earth, and Earth is not having the same heat capacity as water. This was my words. You can see more information on the task 45 website, the fact sheets we made in this task, and we are now updating these fact sheets, and you'll soon see updated fact sheets on the task 55 website. Thank you very much for your attention.
Thank you, Jan Erik. I think this was a very good overview and very impressive, especially what costs are concerned. Very good for investors if cost curves are going down. Thank you very much. Our next speaker comes from Germany. It's Dr. Inge Karin Rühling. She looks back at more than 30 years of research in heat supply technologies. Currently, she is professor in the field of building energy systems and heat supply at the Technical University Dresden, and she is senior researcher at the Institute of Power Engineering. So her speech today is Decentralized Feed-in Existing District Heating Networks, Comparison of Hydraulic Effects of Solar Thermal and CSPH Integration. Here we go. Her presentation is online. And Karin, please, your presentation.
Thank you very much, Bärbel from Dresden. Nice to meet you indirectly, all of you in the part of the world, 243 persons actually, CC currently. My wonderful young colleagues, Ben and Christoph, are assist me in this conference, and I hope you can understand us very well. What we will show you, let's start with the focus of the study and some general effects concerning the tools and the methods in generally. The main focus, how you can see, are existing district heating networks. What we want to do, we want to identify thermohydraulic impacts of more than one. That means up to 24 decentralized feed-in systems in varying in size and position in a system. We compared also not only solar thermal systems, also the possibilities and limitations of decentralized combined heat and power units. What we want to investigate, we want to show resulting requirements for components like pumps, pipes, pressure maintenance, e.g. in the existing district heating network. As tools, we use Trends CUD and the Daimler with new types we developed by our own, and both tools are combined via FME master. What we do, quasi-dynamic annual simulations of the whole network, the feed-in values and the end-user behavior in, that means mass, flow, temperatures for a whole year, and so we see results for energetic aspects, temperatures, pressures, mass flow, and so on. Time steps, we use a quarter of an hour, and we investigate two different networks, two different weather conditions in Germany, Würzburg and Potsdam. Würzburg for more effect on good solar thermal situation, and Potsdam is the average weather situation in Germany. The consideration of a central heat storage as part of the network control strategy is integrated also. The considered networks are two, the network G and the network B. Both are existing real systems in Germany, a third generation district heating network with supply line temperatures in winter up to 90 degrees centigrade and in summer up to 65 degrees centigrade. in the most cases, we had to reach with feed-in temperatures higher than 70-75 degrees centigrade. The NetB is a bigger one, second generation meshed district heating network you see, and the supply line temperatures are higher. That means we had to reach in feed-in situations for solar thermal purposes up to 110 degrees centigrade in the time of spring and autumn. What are our boundary conditions for the simulation? We investigate up to 5 solar thermal decentralized feed-in variants. We start with a small size NetG with a G with 5 times 100 square meters. That means round about 0.35 megawatt peak thermal. And in the NetB, we investigate a higher performance for the summary of the 4 versions of solar thermal decentralized feed-in, starting with 10 times 500 square meters up to 24 decentralized heat producers with, in summary, 2,700 square meters. That means up to around about 19 megawatt peak thermal. Compared with a solution based on natural gas, block heat and power units, that means we compared with up to 5.8 megawatt thermal input into the district heating network. Additionally, we had to make a good consumer modeling. These are models based on regression models for 4 types of buildings, and we calculate the real action in depending on the supply line temperature of the district heating network. We make results for the return line temperature of the customer and the 7 variations of the simulation study at the left-hand side.
So it looks like we lost the sound on Karin, but we might get it back in a second. So everybody, please hang in there.
Variance for solar thermal variance, we reach up to 9% fraction of decentralized production. Higher for our both CHP variants. That means we have in the summertime, the customer side of the CHP, the decentralized feed-in, use your produced heat, not in summertime by its own, but in wintertime. They use their produced heat primarily in their own building or so on. What we can also see in the right-hand side, if we reach up to 52% in the version of 27,000 square meters solar thermal installations, we reach daily fractions up to 95% in some. What are the possible effects of feed-in our system of thermohydraulic effects? We see flow reversals in part of net segments, and this is a normal situation for meshed parts, but for the radial district heating parts, these are only effects of decentralized feed-in. We see also moving supplier frontiers. This means the border between positive and negative mass flows in the pipe. That means the volume flow is round about 0. And what we want to investigate is thermal stress to alternating temperatures. What we reach also, we reach temporarily 4 hours, for 2 hours, 3 hours full supply by decentralized heat producers. We have a high performance of solar thermal. That means low demand at the end user side. That means we need central storages. What we occur also switching index circuit due to change pressure conditions in the network. That means we need a new control methods for central district heating pumps, and we have to take into account the influence on pressure maintenance. Now we will show an example for results of our thermohydraulic simulations. We use the variant of the 27,000 square meter solar thermal installations, and at first we show you the results along this red colored line from CE to SE at the end of the branch 1 in the system. What you can see, gray colored, the central heat producer, central heat generator. What we see, the balls without color inside, these are normal consumers without decentralized feed-in. The little bit brown colored are the 500 square meters solar thermal feed-in, additional with the customer at the same side. The red balls are the 1,000 square meters, and the orange balls are the 5,000 square meters. What we can see if we look at the results for 1 week in July, at the end of June and the starting of July, above you can see the blue line for the production of the central heat generator in the network, and you see the gaps. We filled with the red lined decentralized feed-in of 500,000 and 5,000 square meters. And at the bottom you can see the results in the so-called carpet plot. The epsilon axis is along the branch. The situation we start as central heat generation and end at the end of the branch SE. And what we can see the time at the x-axis. And though we find the blue colored line, these are mass flows from positive values, round about a little more blue-gray. These are mass flows round about 0 or a little bit switched, and red colored, these are negative values. And though you can see with our central storages, we have the red colored situation. We have stagnation in the solar thermal plants without the central storage, but we integrate the central storage, so it's possible to handle with all the energy inside the system. Additionally, we want to show you some results concerning the temperatures at the supply line from 0 to 35 and the return line from 36 to 17. These show us the customers react with the change return line temperatures. This here you see is more blue line. In the cases of feed-in, we see more gray line temperatures. At the right-hand side, you see the coloring. The supply line temperature drops in the direction of the supplier front, a little bit more red. That depends on the situation because we feed in with a nominal supply line temperature from the central heat generator as an aim for our control of the decentralized feed-in. We see the effects on the pipelines and network pumps as well as changes in working cycles, pressure maintenance. All these we can identify. Our short conclusions, we reach annual solar fractions up to 9.2% in network B with 27,000 square meters. The flow reversal and fully supply by the decentralized feed-in of solar thermal plants we identified. We can make a pre-dimensioning for central storages. What we investigate also the combination of heat with combined heat and power production. What's our outlook? We want to make more simulation with network B or with a standalone solar thermal plant in the range of 25 to 50,000 square meters. We want to make prediction of consequences for the central producers concerning the part load efficiency and the CO2 emissions. We want to identify the requirements for the pump and make investigations regarding the thermal stress. The lifetime of the district heating tubes means the district heating pipes. At the end of our presentation, we hope we can show you a short video for all our results in for our for our results of our simulation. This is a short overview over 4 days. We start at one day in July, the 2nd of July. The ambient temperature is around about 23 degrees centigrade, the supply line temperature 80 degrees centigrade, and we have in Germany high return line temperatures in normal district heating systems up to now 63 degrees centigrade. What you can see in this left figure, our heat output, the central production in gray, in blue, the sum of our decentralized customers, in green, the heat into the storage, the stored energy, and what we see also, the central heat generation of the decentralized solar thermal plant in yellow color. Additionally, you see the development of heat losses in the whole district heating network as a value. Here in the middle of the video, so you see the changing of the heat storage situation in percentage of load, the state of charge, and you see in the next slide the variation of the values for central energy and decentral energy itself. The decentralized heat generators are orange colored, and the index circuit point you see in this value. This is the longest way with the highest pressure differences in the network. On the right hand side, you will see the colors for the mass flow. This is a little bit cut because we want to show you the effects concerning our supplier frontier. That means the mass flow around 0. The real mass flow is a maximum up to 100 kilograms per second. Let's start a little bit with our simulation. You will see we start in the nighttime of the 2nd of July. All is blue. We supply from the central heat producer to all, but we start in, I stop a little bit. We start and in the middle of the day before the maximum of the solar power plants, as solar thermal plants we reach, the whole network was supplied from the decentralized situated solar thermal power plant, all is orange, and from these parts we supply the customers as this part of the system. Let us start again. The storage is fulfilled up to round about 80% state of charge, and at the night time we use the central storage to deliver to the system and can lowering the part of the central feed-in. At the morning time we need only a small part of central energy because the feed-in of solar thermal power plants increases with the increase of solar thermal input over the day. And though, let us go forward, and though again and again the same. In this kinds of days in July, we have a fixed index circuit point, but in other situations, for instance, in spring and autumn, we say a change of this index circuit point. This is all what we can present to you today. And so we can say from Germany, from Dresden, thank you for your attention. And if you are interested in, contact us. Thank you very much.
Thank you, Karin. Very interesting. I think for dense cities where we want to establish solar district heating, it's very important to look into these decentralized ways of feeding solar heat into grids. Well, we have the next speaker has an interesting bio because he combines two very important district heating markets, China and Denmark. It's Dr. Chua Ngoc Phan. He works currently as associated professor at the Department of Civil Engineering at the Technical University of Denmark. And his focus areas there are solar heating systems and energy storages. And beforehand, he was researcher at the renowned University Tsinghua in Beijing. So his presentation today will be about the integration of different renewables in solar district heating plants. Welcome, and please, your presentation.
Okay, thank you. Thank you, Barbara, for this introduction. Yeah, I will talk about the integration of different renewable technologies or renewable energies in solar heating plant. So in my presentation, I will first try to summarize the different types of solar district heating systems. Then I will give some examples of the typical type of heating system. And then the first type I would like to talk, that is the direct feed-in. As Karin has just mentioned, in Germany, there are different kind of feed-in system. And then the idea about this feed-in system, what I'm talking about, that is the connection of solar collector field directly with a district heating network. What I mean here by directly, it doesn't mean that it is directly connected. What I mean is that there's no heat storage. This system has no heat storage. And in between the solar collector field and the district heating network, there are, of course, heat exchangers to separate them. And for this system, typically the solar fraction is quite low. It's lower than 20%. This is because to avoid overheating in summer, the solar collector field should not be designed too large. And of course, as mentioned in Karin's presentation, the operating temperature in this system could be different. The operating temperature in some district heating systems in Germany can go up to 100, 110 degrees, while in Denmark, the operating temperature is quite low. For the district heating network, it's around 80 degrees. That means the solar collector field will produce temperature a little bit above this temperature, and then the heat can be directly feed into the district heating network. And this is one example in Sweden, where you can see the above picture, the 270 square meter of silicon solar collector installed in a school, and then the heat will be feed into the network. In summer, the surplus heat from the system will be fed into the district heating network. Well, in the other seasons, of course, the heat from the solar heating system will be used to cover the demand in the school and also compensated by the heat from the district heating network. And then the second type is include short-term heat storage. The difference is that the typical volume for this short-term storage is lower than 7,000 cubic meters. And typically, this will give an energy storage for a couple of days up to 1 week. And the auxiliary energy for this system typically will be, like in Denmark, gas-fired combined heat and power generator, and or a biomass boiler or other renewable technologies. And the solar fraction for this system can be a little bit higher, but it still is quite low because the system cannot store the heat for long term, so the stored heat amount will be quite small. To avoid overheating, the solar collector field should not be too large. And this is one good example for this system with a short-term heat storage. In Jægerspris in Denmark, we can see a broad view of the plant. The solar collector field is 13,000 square meters, flat plate solar collectors connected to the plant, where there are 3 tanks. Altogether, the volume is about 5,000 cubic meters. And we can also see that the plant has a gas combined heat and power generator, and also there's newly installed absorption heat pump in the plant. The plant supply heat for the town with 1,300 consumers. The annual heat consumption is about 27 gigawatt hour per year. And then type 3, that is a system with a long-term heat storage. For long-term heat storage, the volume is typically much larger than short-term heat storage. It's like more than 10,000 square meters, cubic meters. And then this storage could be pit water storage. It could also be borehole storage, soil storage. And for this system, because of the long-term storage, because of the large volume of the storage, the heat can be stored for a long time, and then that will increase the solar fraction of the system. So typically the system solar fraction can be up to 50% or even higher. For this system there will be heat pump to boost up the temperature of the storage. There will be also backup boilers, which can be biomass or gas-fired CHP. And this is one example, as mentioned by Sabina in the Task 55 project. And this is a project in China, which is realized by Argon Sunmark and Sunrise. And this is a very typical system in China because this district heating system does not produce electricity. So only heat is produced. And we can see that the system has around more than 20,000 square meters of solar collectors, and the storage is about 15,000 cubic meters. And the system provides heat for a ton for with a floor area about 80,000 square meters. And then the integration of solar into a district heating system, the type number 4, that is combination of solar and combined heat and power generation. And this is also the system could include a long-term heat storage. And the fuel used for this CHP generator could be gas, diesel, could also be wood chips or other biomass. I will give one example on this type of system. And first, this is like a slide shows you the benefit of a smart heat storage. Just as Jan-Erik has mentioned, a smart heat storage is very important for such a system because of the long-term storage, because of the large volume, a large amount of heat produced by the solar collectors in summer, where there's a limited heat consumption, will be stored in the storage, and this heat can be kept long, can be utilized later over seasons in autumn and in winter for heating of the network. And also because of the large volume, heat from the waste heat from the CHP generator, gas motor, could also be stored in the storage. Therefore, the electricity production and heat production can be decoupled. So that means when there's a very low electricity price, it is not economy for the plant to produce electricity. Then the generator could be closed, but the heat can be taken from the heat storage and use it to supply heat for the consumers. While when the electricity price is quite high, and then the heat can be generated, or the waste heat can be generated by the CHP generator and will be stored in the storage. And in the periods where there's low price of electricity, the heat pump can also be activated, and the heat pump will boost up the lower temperature in the storage and use it directly for heating for the network. So you can see that the heat storage gives the flexibility. This makes the combination of different renewable technologies, renewable sources possible. And of course, because use of the cheap electricity, the economy of the system could be optimized. And this is one example, like the Marstal Solar heating plant Jan-Erik has already mentioned, but I will focus on the system point of view. And we can see that for this system, there's wood pit storage and solar collector field, and in the system, the boiler use wood chip boiler combined with ORC, which can generate electricity. For this system, it also use a CO2 heat pump. The solar fraction for the system around 40% or even higher to 50%, depends on the different years. It is because of the heat storage, the well integration and interplay of different renewable sources could be realized. I will spend some slides on details of this system. And this is a bird view of the system. this is a Marstal Solar heating plant. We can see there are altogether 3 collector fields, altogether up to 33,000 square meters of solar collectors, while the heat storage is about 75,000 cubic meters. It's a watt peak heat storage over here. And then in the plant, in the technical buildings, there are biomass boilers, ORC units, and CO2 heat pump. The system provides heat for the town, Marstal, with a number of consumers like 1,600. The annual heat consumption for the system is around 30 gigawatt hour. So I will share with you some of the monitored data of the system. And first, I will want to show you the picture of the heat pump. It is a CO2 heat pump with a heat output 1.5 megawatt, and there are altogether 16 compressors. And the district heating forward temperature is 45, and the return temperature 35 degrees Celsius. The average COP for this heat pump is around 3.4 or 3.5. And this is the monthly heat balance in the Marstal Solar district heating plant in 2015. And this is a result of an EUDP project here in Denmark, which is carried out together with Plan Energy and Solitas. And from this draw, we can see the heat balance for each month of the year 2015. And from this, we can also see that the yellow, the bars in yellow, that's the production from solar collectors. And it is most production is in the summer and maybe also the late spring. And the production for the biomass boiler, that's mostly in winter and autumn. But we can also see the contribution from the watt peak storage. That's shown in pink. It is mainly in the autumn and also in early spring and winter. And also we can see the electricity consumption of the heat pump shown in red. It is in the winter, where when the temperature of the watt peak storage is too low to be supplied directly to the district heating network, then heat pump is necessary to boost up the temperature. From this, we can see that by combination of different renewables, and it's possible to cover the demand for the whole city. And this is a monthly solar heat production, and we can see that, of course, in summer there's a lot of sunshine, and then solar production is quite high compared to the rest of the year. But what is interesting is for April, we can see that this year in April we have the largest monthly solar heat production. The reason for this high solar production is, of course, that year the solar radiation is quite strong. But another important reason is that because of the use of the heat pump, the temperature in the watt peak storage is decreased to quite a low level, like 10, 15, or 20 degrees. And because of this low temperature level, and then the efficiency of the solar collector could be increased, then result in a higher solar production in April. And this is operation conditions of the heat pump for the year. We can see that the heat pump, the outlet temperature is quite stable. It's like 75 degrees, and the condenser's inlet temperature is somewhere between 35 to 40. That is the return temperature from the district heating network. And then for the evaporator side, Then the temp that is also from the heat storage side. The inlet temperature is sometimes 50, 30, even to 60 degrees Celsius. While the temperature back to the watt storage, watt peak storage, that is around 20 to 30 degree. The annual COP is around 3.0 to 3.5 if we see the average. And this is this slide shows you the energy flow diagrams in 2015, and we can see that for this year the solar fraction is around 40%, and among this contribution from solar, some part is directly from the solar collector to the buffer tank and to the network and to be utilized, and some of it will be utilized further, will be stored further by the long-term storage, the watt peak storage, and then used later. And some part is first boost up the temperature by the heat pump and then used. Of course, there's some part will be lost to the ambient. And then here at DTU, we have developed the models for such a system, which can enable optimization of a solar heating system. In this system, you can see that we have the solar collector fields, and we have the watt peak storage. We have both the short-term and long-term storage included. We also have the different heat pumps and also the ORC unit included. For this system, we have the major major component of the solar heating system included, so we can make like a calculation of the yearly thermal performance of the system with different parameters. Therefore, we can use it to design and to optimize such a combination of different renewables. By this, this is the end of my presentation. Thank you for your attention.
Thank you, Fan. Oh, this was indeed a comprehensive one on different combinations. We have a bit an issue with the time, but I still would like to have our last speaker and hope that all our participants might be available a bit like 5 minutes longer to have also some questions at the end. Because we have a very interesting presentation at the last from Lucio Mesquita from Canada, because he's talking about a Canadian solar district heating project, which is quite famous because it reached 100 solar fraction in space heating in winter 2015-16. Lucio Mesquita is responsible for sort of operating this system and monitoring it over the years. He has designed and commissioned more than 180 commercial solar thermal projects and is one of the North American leading experts on solar cooling systems. And he's working since March 2016 as Senior Energy Solar Thermal expert at CanMed Energy, which is like a research lab for the Canadian federal government. So we will hear his presentation on Drake Landing, a high solar fraction district heating system. Lucio, it's yours is the floor.
Thank you, Barbara, and thank you for all participating today. Yes, CanMed Energy is a research and technology organization within the Ministry of Natural Resources in Canada. And we have 3 labs throughout Canada, and I'm part of the Renewable Heat and Power Group. Drake Landing, which will be our focus today, was conceived at a small community, a pilot project. We have 52 houses in Drake Landing, designed for high solar fraction, which was a bit different from everything we had at that time. And it was done under the leadership of Natural Resources Canada. Doug McLean was our manager at that time, with local partners. You know, the ATCO is the local gas utility, the town itself. United Communities was a developer, and Sterling Homes, the builder. They all had a very important participation in developing and are still participating in the operation of the system today. There is a large imbalance of between the solar radiation and the space heating load in Canada and most of the northern countries, as is well known. And that was the main idea for creating a high solar fraction system with seasonal thermal storage. Drake Landing was built in 2005 to about 2007, then it started operation. And again, as Jan-Erik has mentioned in some of his presentations, this is a very small system, so it was built as a proof of concept, a small pilot. Okotoks is in Alberta, a fairly high latitude, very close to the Rocky Mountains. It's a very interesting place, a small town, 28,000 inhabitants, at the foothills of the Rocky Mountains. As we can see here, this is the array, and right on the back here, this is looking on to the west from the energy center. We can see the Rocky Mountains. So just to compare a little bit in terms of climate, as we can see in terms of heating degree days, Drake Landing would have, or Calgary, Drake Landing and Okotoks are just about 50 kilometers south of Calgary. As you can see, a very cold climate, very high level of heating degree days, but also a sunny place. Right? So much colder than most of the European countries on that, all the European countries in that table, but also with higher levels of irradiation. This is a schematic of the system in Okotoks. We have 4 blocks with 798 collectors, so fairly small in terms of what we have seen today of large district heating systems. And that energy is then gathered in short-term storage tanks and then transferred to the boreholes. So we have a seasonal borehole thermal energy storage system with 144 boreholes, 35 meters deep, and they occupy at 35 diameter. And separately, we have solar water heaters for the house. So the central system for Drake Landing does not supply domestic hot water. Domestic hot water is separated and individual for each house, where we have a 2 collector system preheating the hot water for a gas water heater. So we don't have heat pumps. This system was designed as an ultra low temperature district heating system. Most of the time it supplies heat to the house at 37 degrees and it returns at about 28. So that's quite different from most of what we have seen today. And here is a picture of the community, the 52 houses and the 4 blocks. And what we can see here, the blocks, and to the right, top right side of the picture, we'll see the energy center. And then to the right of the energy center, we have the borehole field. And so we can see the borehole field that does not have installations on the side or bottom, but it does have insulation at the top and a good level of insulation, as we are not seeing there any melting from the snow in that area. So this is the area of the borehole field. So this is the borehole under construction back in 2005, which was a bit of an adventure because the area had a very strong rain around this time. So this became a pond for a while until it was to drain this. But there we can see the heat flow goes from the center to the outskirts of the borehole field. That way the center is always hotter than the outskirts of the borehole field. And this is a picture, a more current picture. The area is now a park, which is an interesting point regarding a borehole thermal energy storage technology, is that the area above the energy storage can be used as a park, and it is the case at Drake Landing. Most of the houses in North America, they use air in terms of heating and cooling. And in the case of Drake Landing, then it was necessary to design a specific design for that project that could supply heat even at lower temperatures. You know, although the maximum design temperature shown here is 55, as I said, most of the time the heat comes in at 37 degrees, and then it supplies heat to the house through air ducts, which is the common way of doing it in North America. So it's not a hydronic system. The system was designed based on building simulations, and we have the help from our buildings colleagues to design and evaluate the heat load for those houses. The house had a higher level efficient than the house that were typically built in that area at that time. And the system was then simulated in transit, you know, to optimize the design and evaluate the parameters of design and operation. And since the beginning, it has been monitored. So Drake Landing has been operational now for 12 years. So we have 12 years of a fairly extensive data on its operation. This graph shows the individual heat load for each one of the 52 houses. That's the average for the last 5 years. And it's interesting because, you know, I have worked on the design of many individual space heating, solar space heating, solar water heating systems. And what we can see here is that the average is very close to what we had estimated at the beginning of the project. But in the individual meter heat usage is quite different. So if those systems were individual, we would have a big problem, but we don't, because we are working on a community scale, and that's the beauty of community systems. And so that's an interesting aspect and interesting point to remember. On the left here, what we have is the set point supply for the air handlers for the district heating system. As I mentioned, most of the time we operate at a 37 degrees. And then once the temperature goes below -4, and then the supply temperature goes up. And in this area, it's not uncommon to reach -30 in terms of ambient temperature. So at that point, we will supply at around 50. So this is the set point, and what we can see here on the other side is the measured supply and return temperatures. And so, as you can see, most of the time we are supplying at around 37 degrees and the return at 28. So this is important because this will increase the efficiency of the solar collectors and also increases the available energy in the borehole thermal energy storage, even without the use of a heat pump. And talking about the borehole thermal energy storage, those are the temperatures for the borehole. There's a couple years there where you can see usually, you know, it gets heated all the way to a little bit over 70 degrees, and then we extract that energy in the winter, and the borehole will go down to around 40. So, you know, there would be possible to have a combination with the heat pump. It wasn't part of the original design, so that if we were using a heat pump, that temperature would come down even lower, right? But that was not the case in terms of the design. But we have there about 30 degrees delta T in terms of effective storage. In terms of the COP, that means how much energy we are supplying and how much electricity we are using for pumps, so we have two different COPs. One is the COPs limited to the electricity for solar and the storage pumps, and then the electricity for all pumps, which now includes the district heating system. So the system operates with a fairly high COP, you know, usually around 30, and the electricity used for the pumps is offset by a PV system on the roof of the energy center. In terms of general performance, what we have there, we have three curves. The green one is the simulated performance based on the same year, if we simulate the same year for 50 years. The blue one is the simulated with historical weather, and the red one is the actual performance of the system. So the system is performing according to what we had expected. We are going to beat around 91% for this winter, which is now ending. And as Babel had mentioned, we did hit 100% back in 2015, 2016. So the system is performing as expected. Conclusions. I think the first thing to say is, a lot of people say, well, when is that going to be replicated? We have an environment in North America at the moment with very low natural gas prices, most of the time, in most places, below 5 cents per kilowatt hour energy for natural gas, and actually in other places below 3 or even 2. So it's at the moment it's very hard to compete against natural gas, but the system has operated reliably and has performed well, and we have looked into larger systems. We're still trying to replicate that into a system that would have a much larger borehole field. We have about 45% thermal efficiency of the borehole field. If we had more than 1,000 units, 1,000 homes to supply, that efficiency would go up to around 80%, as young Eric has shown in his presentation. And we're also evaluating other opportunities in terms of brake landing. One of them is, to try new technologies, for example, to implement a heat pump into the system at a mix of PV, east, and solar thermal. And just to finish, Drake Landing has a website with more information for those of you that are interested. There is also an app which shows the current conditions, which I'm going to show here, which is also part of the website. And there we can see the current conditions in Okotoks at the moment. 1 degree ambient temperature, short-term storage tank top about 65 degrees, and the borehole field, which we are already starting to charge at this time of the year. But just a last word, we are probably going to discontinue both the app and the live data for the website in a few weeks. It's not going to be part of the website anymore. And with that, I will finish, and thank you very much all for the participation. Thank you, Barbara.
Thank you, Lucio. Very interesting. Maybe directly a question to you, because it just was raised. How do you heat houses with this low district heating temperatures?
It's all on the design, right? The house have set points of 21, 22 degrees. So if you design the fan coil appropriately, you can do the work with only 37 degrees water. So
because it's new build. Okay.
Yes, we won't be able to do that if we have a node design with radiators. Right? That wouldn't be possible.
Yes. Well, thank you, everybody. It was a very interesting run through a lot of different projects. The first question goes to Karin Rühling. What fraction of German district heating networks can be upgraded to lower system temperatures like this type generation 4?
Lowering up to the level of fourth generation?
Yes, that means going with... Yes.
Oh, this is not so easy to say. There are hydraulic limitations because we had to take into account that we are limited concerning the high return line temperatures in German district heating networks. Only in these cases where customers change the supply system from normal radiators to floor heating or activating of the wall of buildings, then we can lowering the system temperature. And the high part is also the domestic hot water production. In Germany, we have today the the context of nominal 60 degrees centigrade in the supply line of domestic hot water. That means we need also in summertime 65 degrees centigrade in the supply line, and it becomes in circulation situations in the domestic hot water in the nighttime, mainly in summertime, around about 55 degrees centigrade and more. That is a limitation in Germany. All energy suppliers work in the so-called district heating network 4.0 initiative on lowering the temperatures. But we think lowering more than in the range of 195 degrees centigrade is not possible inside the next 10 years.
Okay, thank you. We have here questions for Fan regarding benchmarking flat plate collector fields and prices in China. Can you say something about that?
Okay, yes. In China, so far as I know, there's no large production of these flat plate solar collectors for district heating use. So most of these collectors are collect small collectors with an area of 2 to 4 square meters, and they are mainly for use of domestic hot water. So I don't know the price, so because it's not existing, but I can predict that if China with a mass production of this collector, the price will be lower than the price in Europe.
Okay, well, maybe Jan-Erik, you give us the benchmark price of a typical large-scale green grass field in Denmark per square meter.
Yes, that will be around 200 euros per square meter for the whole system in operation.
Okay, so this is the benchmark for Denmark. Fen, how about, there's one question which might concern you as well, because it's going into the direction of evacuated tubes. What is the efficiency of flat plate collectors for 110 to 65 degree networks? And is evacuated tube collectors more suitable for this application? Have you studied that?
Yes, of course, in practice in Denmark, the district heating system has a lower temperature. Between 80 and 40 degrees. So in Denmark, we don't have any system which operates at a higher temperature of 110 for flat plate solar collector. But I could, we have investigated a combination of flat plate solar collector with parabolic trough collector. So the flat plate collector will preheat the water, and then afterwards the water will be heated up by the parabolic trough collector. So far we haven't used, as far as I know, there's no system use evacuated tubular collector in district heating, because well,
there are some in Germany, however.
Not in Denmark as far as no.
Not in Denmark, yes.
Yeah.
Okay. I have a question for Jan-Erik. How about the difference in heat losses between the Droningland storage and the Marstal storage? This came out of your presentation, and this participant wondered about these huge differences.
Yes, so in Dronninglund we have lower temperatures, and also it's more used, more frequently used, so there's more input and outputs compared to the storage capacity. And also it has a very good insulation in the lid and dry. So this is a very good system, yes.
Okay. You were also asked whether you have calculated LCOH values, levelized cost of heat values, only for the storage. Have you?
I have not, but well, you can see in the figures that if you make the storage and the system very large, you have same heat price as for the smaller simple systems.
Okay. And the last question for you was the overall comparison, again, between solar thermal, a large field, and a thermal tank, and a PV solution with a heat pump. Have you ever looked at the overall efficiency and cost advantages of one or the other solution?
So looking at the efficiency towards the incoming radiation, it will be more or less the same as the solar collectors has maybe 3 times higher efficiency, and then on the PV you have a heat pump with a COP of 3 maybe, so the efficiency is the same. But I did not look into details of the PV system prices, so on the economic side I will not give an answer in this forum.
Okay. Well, we had somebody asking for activities in the US in terms of district heating. Lucio, you are based at least in Canada, which is close to the US. Can you say something about district heating, solar district heating activities in the US? Unmute yourself.
There is very low activity, and that's mostly due to the low price of natural gas throughout North America. Even though there are a reasonable good number of district heating systems, small ones, mostly related to university campus and some downtown areas. And I think that's another point too, is that in North America, most of the district heating systems, they are in areas that are high density, so it's very difficult to find the area for installation of a solar system.
Okay, and there's another question regarding your figure. Somebody says, please confirm the diameter of your borehole storage. Is this 35 meters or 33.5 meter?
35 meters. Yeah. 35 meters for the total field, right? Not each borehole.
Yes. Okay. So maybe Jan Erik, there's again a question on benchmarking costs. You know, we have talked about capex cost for fields, which in Denmark are about 100 euro per square meter. Now the question rises for OPEX costs, like operational costs. Can you give this maybe as a percentage of the investment costs, or how is that calculated in Denmark?
So normally we calculate it as between 0.5% and 1% on the performance. So for electricity, we use maybe 0.5% in the pumping as the performance of the system. So very low maintenance costs. And we have systems running for 30 years now.
Okay. Very well. Karin, last question for you as well. Somebody asked, what is the limitation in the smallest area sort of that needs to be well connected with a district heating system? What makes sense if you compare the overall costs and the feed-in components?
Yes, thank you for the question. In our German situations in existing district heating networks, we say around about 200 square meters are the minimum for so-called secondary networks. That means parameters at the supply line up to 75 degrees centigrade, and the pressure level, the so-called PN level, up to 10 bars and lower, and better are 500 square meters and more for the higher network parameters. This is mainly due to the high cost of the feed-in substation, not from the solar thermal or CHP side. It's mainly in high costs for the feed-in pumps at the network side of the feed-in substation.
Okay, thank you. The last question, which is a bit more service-oriented, maybe Jan Erik, a question of ready-to-use software to simulate solar district heating plants.
Well, we use for this seasonal storage plants, we use Transys, and we use for more normal systems, we use a software called Energy Pro, which calculates the energy systems for district heating supply in general.
Okay, well, Thank you so much. We run a bit out of time. We are 6 minutes past. So I would like to close at this point. Thank all the speakers for their very interesting presentations. All presentations and the recording will be available on the ISES website and on the Solar Academy website. So you can check that in maybe 24 hours or something. It will be available. Well, have a nice afternoon, everybody. And I hand over to Arabella for the last final words. Thank you very much.
Yes, thank you very much, Bärbel, and thank you a lot to all of our speakers who found the time and joined us today. I think we have heard some great presentations, and I can see from the audience engagement that you all very much enjoyed it. So there's one quite a big information or announcement I'd like to say before we finally end the webinar. So there's a very important event coming up actually for both ISES and the IEA SHC at the end of the year, and this is the Solar World Congress 2019 in November in Chile, together with the International Conference on Solar Heating and Cooling for Buildings and Industry by the SHC. So that's the big conference for them in 2019 as well. This event consists of plenary speeches, presentations, forums, workshops, social events, technical tours, and more. And within this big event, there will also be featured the 9th International Conference on Solar Air Conditioning. That's the SAC 2019. And for this big congress, the deadline for abstract submissions is still open. It closes, attention, tomorrow at 22nd of March. So if you still want to submit your abstract for this conference, for this big congress, please submit it until tomorrow. You can find all information on the two websites. So that's the swc2019.org and the shc2019.org. And I think on behalf of both ISES and the IEA SHC, we are very much looking forward to meeting all of you there and to have as many people join us for this awesome event. And then for my final announcement, there will, of course, as Bärbel said, be a recording of the webinar. And usually it takes us about 1 to 2 days to get it online, and you can then find the recording as well as all of our presentations that were given today, both on the ISES homepage and the IEA SHC Solar Academy homepage. So within 1 or 2 days, you should be able to access the recordings there. And for ISES members, please remember you already have the unlimited access to all past webinar recordings and all past webinar presentations through the ISES members area. And now, on behalf of ISES, I'd like to thank all of you, and of course, thank you again to our great set of speakers for your participation in today's webinar. We are always looking forward to your feedback, so you can write to us at public.relations@ises.org, and we invite you to complete the survey, which you will receive as a follow-up to the webinar. So thank you again to everybody who joined us today. We will now end the webinar, and we wish you a great day. Goodbye, everybody.